students, welcome to experiencetutor.com. Today we'll discuss about class 12 chemistry chapter solid state part 11. And this is our welcome message. Today's topic is close packing in ionic compounds. Radius ratio. So, for the stability of ionic compounds, each cation should be surrounded by maximum number of anions and void anions, and vice versa. The maximum number of oppositely charged ions surrounded each ion is called coordination number for that ion. Since ionic bonds are non-directional, the arrangement of ions in the crystal is determined by sizes. The ratio of the radius of the cation to that of an ion is called radius ratio. So what is the radius ratio? If you write the formula, radius ratio is equal to radius of the cation upon radius of the anion. Radius of the cation or radius of the anions, that is R minus. Eventually, greater is the radius ratio, the larger is the size of the cation, and hence the greater is the coordination number. The relationship between the radius ratio and the coordination number and the structural arrangement are called radius ratio rules. So, what is this rule? What are these rules? So, if the radius ratio is in between 0.155 to 0.225, then coordination number will be equal to 3. Structural arrangement will be trigonal planar. And type will be B2O3, example is you can take B2O3 as an example. Similarly, the second rule is if the radius ratio RR is in between 0.225 to 0.5 414, then coordination number Cn is 4 and structural alignment is tetrahedral. Tetrahedral, and type will be ZNS. Example can be ZNS, CUCL, CUBR, CUI, HGS. The third rule, if the radius ratio is in between 0.414, 0.414 to 0.732, then coordination number is 6. Structural arrangement is octahedral. Octahedral. Type will be NaCl. Example can be NaCl, MgO, NaBr, CaO, etc. Now the fourth and last type, that is, if the radius ratio is in between 0.732 to 1, then coordination number is 8 and structural arrangement is cubic. Type is CSCl. Example can be CSCl, CSBr, NH4Br. So these are the four rules. These are the four rules for radius ratio. The above results may be further understood with the following explanation. The most stable arrangement is one in which anions are touching each other as well as the cations simultaneously. Thus, stable arrangement for the planar triangular structure is shown below. So, let us go to the next slide. let us see the structures first. So three cases are there. Here is the first case where three anions are there, are touching each other. This is A. Second, we can write this little bit separated with each other. Here, all the three spheres are touching a cation. So in this way. So this is B, and again three spheres are there touching each other. So this is the figure 3. Now let me explain this. If the size of the cation increases, keep the size of the anion same. Before that, let us understand something. The most stable arrangement is one in which the anions are touching each other as well as the cation simultaneously. Thus, the stable arrangement for the planar triangular structure is shown in the figure. Now, if the size of the cation increases, keeping the size of the anion same so that the radius of the radius ratio increases, we observe that the cations are no longer touching each other. Anions are no longer touching each other as shown in the figure B. So this explains the figure B. First one explains the figure A, where the most stable condition where the anions are touching each other. And the second condition, so here you can say that here cation, this is the cation here, and it is touching all the three spheres. So this is the most stable state, A. And B, where the cation size is increasing. So now the anions are not touching each other anymore. So this is the figure B. And figure C, or before going to figure C, we should understand figure B. Hence, they adjust themselves so that they are touching each other as well as the cations. So under such a situation, four anions may be touching the cation as well as each other as shown in the figure C. It leads to tetrahedral arrangement. So as shown in the figure C, it is a tetrahedral structure because four anions are touching the cations as well as they are touching to each other. Now let me explain the octahedral structure. To explain that, I need to draw figures again. So say these are the four anions arranged in this way. In the middle we have a cation. Here this is a here the coordination number is 4 and change to stable tetrahedral arrangement. Now in the next figure now the cation became little bigger, so the spheres will be arranged in this way. And so these are the four anions. Now the cation is little more bigger, so this is touching. This is now not touching each other, so anions are not touching each other. So but they are touching to the cations. In this way it can go on. And in the extreme left it can change to stable tetrahedral arrangement where coordination number is 4 here. So here coordination number is equal to 4 and stable tetrahedral structure. In this case the radius ratio, that is radius of cation upon radius of anion ratio, is less than 0.414. In this case radius ratio is greater than 0.732, and extreme right, the change to stable BCC arrangement where coordination number is 8. So it here coordination number is 8 and BCC arrangement, it changes to BCC arrangement, and in this case it changes to CN coordination number 4. Right here, coordination number 4, and changes to tetrahedron arrangement. And this is here, this structure, octahedral shape, octahedral arrangement. Octahedral arrangement where coordination number CN number is 6 and radius ratio is equal to 0.414 to 0.732. In between, radius ratio is in between 414 to 0.414 to 0.732. Now we'll discuss Pauling ionic radii of some common ions. So Pauling's ionic radii of some common ions. So the cations, if we take the radius as radius in pm picometer, then Li plus have 60, Na plus have 95, potassium plus potassium cation have 133, Rb plus have 148, Cs plus have 160, Mg2 plus have 65, Ca plus have 99, and Al aluminum have 3 plus have 50. If we consider anions, lines. Then F minus have 135, Cl minus have 181, Br minus have 195, iodine minus have 216, O2 minus have 140, and S2 minus have 184. Comparison of calculated. Now comparison of calculated sum of ionic, radii and observed interionic distance. So we can write calculated sum of ionic, radii and observed distance. For NECL, the calculated sum of ionic radii is 276 and observed distance is 281. For KCl, it is calculated sum of ionic radii is 314, observed distance is also 314. For RBCl, the calculated sum of ionic radii is 329 and observed distance is also 329. And for CSCl, the calculated sum of ionic radii is 350 and observed distance is also 347. So we can see that calculated sum of ionic radii is approximately equal to observed distance in most of the cases. And this is the end of this topic. Please subscribe our channel. Please click on the bell icon to get automatic notification when a new video is uploaded. Please comment us on this video and on other videos, and please let us know if you required a new video. Please name the topic in the comment box. We will soon release the video of your topic. Please give us a like sign if this video is helpful for you. Keep on watching experiencetutor.com. Thank you from our team.